Good morning, dear students, and welcome to Vista's Relearning and Online Educational Platform. My name is Denzil, your physics tutor for class 11. So let's get started with today's session. Today we discuss one of the most important concepts in this laws of motion, which is a circular motion. This is a session 8. So when do we say that the object executes a circular motion? It is when an object moves along a circular path. Can you guess of an object which moves along a circular path? Well, I can think of one, that is moon revolving around the earth. The path that it takes is a circular path, and since it moves from one point to other, it executes what is called as a circular motion. Now, another example that is much more closer towards the earth is my favorite, which is the F1 car. The drifting of an F1 car along the circular path. Now, what is more fascinating about this drift is that this F1 car sticks to its path and does not get drifted away from its path. Now, what is the reason this F1 car sticks to its path? Now, there might be plenty of reasons why, but we are going to discuss those reasons why a given object sticks to its circular path and how we can identify those physical quantities. So, another example that I can give you of a circular motion is this athlete throwing a hammer ball. During the Olympics, you have this competition where a hammer ball has to be thrown, and whoever throws the farthest wins. So while this athlete whirls this hammer ball, there's a certain force that is drawing the hammer ball inside, that is keeping it within that circular path. Just like when you take a stone and whirl it. So when you, one moment, I'll use a color. Okay, just like when you take a stone, tie it to a thread, and you rotate it, so that stone will move in a circular path. So this would be the circular path. So what force is acting on the stone to move in its circular path? There has to be some force, and that force is what we call as a centripetal force. Now, how do we define a centripetal force? A force that is directed towards, not forward. A force that is directed towards the center. A force directed towards the center in a circular path. A circular path has a certain radius to it, and along that radius is where the force will be acting. If so is the case, can we derive the expression for centripetal force? Let's derive the expression for it. Now, we know that from a previous lecture, acceleration can be identified. Now, the type of acceleration that I'm discussing here is a centripetal acceleration. Centripetal acceleration are those acceleration directed or seen towards the center, observed acting towards the center of the circle. Centripetal itself means center-seeking acceleration. Center-seeking. Centripetal, center-seeking. So centripetal acceleration, center-seeking acceleration. So AC is the centripetal acceleration, which is given by v squared by r. The derivation of this expression, it is present in the previous lecture. So you can visit us at www.v-learning. There under playlist, you see a lecture that is based on the derivation of this expression of centripetal acceleration. Right, so now that we know centripetal acceleration is v squared by r, then the centripetal force, let's say Fc, which is equals to mass times the acceleration. This is how we usually define force by Newton's second law, by product of mass and acceleration. Also, we can define it by the rate of change in momentum. Now good, we have this expression of a force. Do we know what is centripetal acceleration? Yes, we do. We have centripetal acceleration, which is equals to v squared by r. So the centripetal force is equals to m v squared by r. So this expression is to find centripetal force. This is how you can identify centripetal force. Okay, now that we know how to identify centripetal force, so the same force, the same formula, which is centripetal force, can be used to calculate how much of force is needed for these nice cars to stay in its circular path. So let's take those examples of car moving along a circular path, because it is even more fascinating when you take race cars. But let's take those examples of car moving along the circular path. Now we will consider two different types of road. A car moving along a level road. So motion of a car on a level road. So here we have a car which is moving along the level road, but along a circular track. Now, since it is moving along a circular track, there's a certain force that is acting inwards, which is the centripetal force. That is also mentioned here as F. Good. So next, we need to identify what are the various forces that are acting on the car. So let us try to identify the various forces. So we see that there are three forces acting on the car. One is the weight of the car acting downwards, given by mg. Second, due to the weight of the car, there's a normal force which is acting upward, given by n. And also a centripetal force which is acting inward. That centripetal force has an impending force called the frictional force, which is given by F. So to the impending motion of a centripetal force, you have frictional force acting. So now, since there is no acceleration in the vertical direction, obviously we don't see the car moving up or down. It is only moving sideways, right? So as there is no acceleration in the vertical direction, we can state that n is equals to mg. N, the upward direction motion, is equals to mg. When taken the difference between the two, which is n minus mg, is equals to 0. So the net force acting in a vertical direction is 0. Right, so we have identified the net force acting in vertical direction. Now let us try to identify the force that is acting inwards. That force that is acting inwards is the centripetal force, which is given by mv squared by r. That's quite simple. See, r is the radius. So this is quite simple, mv squared by r. We're done. Is that all we wanted? No. Also, let us try to find what would be the maximum velocity at which this car can move in a circular path. Why are we doing this? Because we want to know, especially during the racing, what will be the maximum velocity a car can move along in a circular track. Because if it exceeds more than the maximum velocity, then the car will not be under control. it will go slam a barricade, or it will move out of the track. So what is the maximum velocity this car can travel along a circular path? To identify that maximum velocity, we already have velocity in the expression. But this force, which is the centripetal force, is equals to the frictional force of an impending motion. So this frictional force is given by mu s times n, where mu s is the static friction, n is the normal, and this is how you identify a frictional force. So I will write it here, that frictional force, which is equals to mu s times n, and this is, as you know, the centripetal. So we need to identify what is v, but n we already know from the previous is equals to mg. So substitute it in place of n, mu s mg, where m on both the sides get cancelled, and you get this v square equals to mu s r into g. So those of you who are still wondering what is mu s is coefficient of static friction. Okay, so that is mu s, coefficient of static friction. Now for those of you having troubling with this expression for friction, you can again go follow the previous lecture where I've taught you about friction, the three different types of friction: static, sliding, and rolling. And among these three, how do we put them in an increasing order of friction? Those things have been discussed in the previous lecture. Visit us at www.v-learning.in. So now we identify the velocity, which is square root of mu s r times g. There you go. So this is how you can identify maximum velocity that a car can travel along a circular path for a level road. All right. So how do I make the best use of this expression? How do I make the best use? How can I make sure that I get the maximum velocity from a car? Well, here's how you can increase the maximum velocity. Well, we cannot help with respect to r, which is the radius of a circular track, is not decided by us. It is decided by an organization. So they construct the circular path, the track that they desire. All right. So radius of that particular circular track, not left to the car races. They don't decide. Acceleration due to gravity, well, nature decides the value. You don't get to decide as well. But one thing that you can vary a little is this coefficient of static friction. Here's how you can do it: by adding spoilers to the car. So when you add spoilers to the car, it increases the downforce of the car. So behind wheels will experience more downforce, therefore there's more grip, hence more static friction in that following case. So that is how you can increase the coefficient of static friction, by adding spoilers. So that is one type of road, which is of a level road like this that we observed. For a level road, the maximum velocity a car can drift. Now we shall look into motion of a car on a banked road. What does it mean for a road to be banked? Now here's an example where a track has a banked road. So the outer edge is extended outwards or upwards, and the inner edge is tilted downwards. So you have this inclination in the road. So these are NASCARs which are moving along a bank road. So what we should do is, we should also identify the maximum velocity for this and then compare it with the maximum velocity for a level road. Are you ready? Okay. So let's take a look at this diagram here, where you have a car that is moving along the bank road. We make note of various forces and its respective components. Various forces are the weight that is acting downwards, given by mg, with its respective component, with its normal acting along this direction, n cos theta, and frictional. You have this centripetal force which is acting inwards, given by F. So here they've mentioned all the various forces, and you have this one component of a centripetal force which is F sine theta. Good. So now that we have this figure where multiple forces have been identified, next what we do is we consider those multiple forces, put them as an form of as an equation form. All right. Now we have a downward force mg and F sine theta. So you have one force which is mg plus F sine theta acting downwards. This force is nullified by an upward force which is n cos theta. Okay. So this is one expression. Not bad, right? We identified one expression which is mg plus F sine theta equals to n cos theta. Similarly, we can identify, this is now we just found for a vertical, now we identify horizontal. For the horizontal, you observe there's one component which is F cos theta and another component which is n sine theta, which is equals to the centripetal force which is mv squared by r. That's pretty straightforward. So now we have two equations. Let's call it equation number 1 and equation number 2. Taking equation number 1, take equation number 1 and equate it to n. Okay. Mg plus, let me write that as mg plus F sine theta is equals to n cos theta. All right. So now in this equation F, this force, let me put that as blue color. This force is a frictional force which can be written as mu s times n. So in both this equation you can substitute mu s times n, but for this I will make sure I equate it to n. So I get mg plus mu s n sine theta is equals to n cos theta. Good. Now we write that mg, take that mu s n sine theta to the other side. So you get n cos theta minus mu s n sine theta, right? Yeah. Since there is no acceleration along the vertical direction, the net force along this must be 0. Don't worry about this one. We have covered this. Don't worry about this. We have already covered this one. Okay. We'll continue with the expression. N is a common factor. So you get this mg equals to cos theta minus mu s sine theta times n. So what should be n equals to? N should be equals to mg by cos theta minus mu s sine theta. That's pretty much. Good. So now we have obtained this normal force. Now this normal force n, we will substitute it in equation 2. Interesting, isn't it? So we substitute it in equation number 2. Right. Put the line there. So writing the equation number 2, let's write that down. F we know is mu s n. Mu s n plus n sine theta plus n sine theta. Oh, mu s n, no, mu s n cos theta. I didn't write that cos theta. Students, you need to remind me. When I miss couple of terms, you need to tell me where I've missed. That's okay, I got this. No problem. Mu s cos theta plus n sine theta is equals to mv square by r. All right. Do we know what is n? Yes, we do. We know what is n. Okay. So first what we'll do is we will simplify this a little. It looks more complicated, right? We will simplify this a little and then we will substitute. So n is a common factor from these two. You get mu s cos theta plus sine theta is equals to mv square by r. Now we can substitute for place of n. What is n? mg cos theta minus mu s sine theta. mg. I'll write this term. Mu s cos theta plus sine theta whole divided by, then the denominator, cos theta minus mu s sine theta is equals to mv square by r. Ooh, that's a big equation. Not too big, but sufficiently large. So we write it here once again. That is mg mu s cos theta plus sine theta divided by cos theta minus mu s sine theta is equals to mv square by r. M and m are the two can get cancelled. M and m can get cancelled. So what you're left with is this. You can multiply, divide cos theta in this numerator and denominator. Okay, in the numerator you divide cos theta, in the denominator also divide cos theta. So by dividing cos theta in the numerator, okay, so you get mu s cos theta by cos theta. Okay, there's some problem here. Plus sine theta by cos theta divided by cos theta by cos theta minus mu s sine theta by sine theta. Okay. Oh, so sine theta by cos theta. We're dividing by cos theta. Now you can cancel the cos theta here, and here. Sine theta by cos theta is tan theta. So this would be v square by r. At this side, I can write this as g, sorry for that, g mu s plus tan theta divided by, hey, come on, tan theta divided by 1 minus mu s tan theta. 1 minus mu s tan theta. This is equal tan theta. This is equals to v square by r. R. Transpose the r there. It is big. It is big. I know it is big. All right. So we are finally there. We are finding the velocity. V square equals to rg. Stop stealing the terms. Don't steal g and things like that. Come on, guys. Help me out here. Tan theta divided by 1 minus, come on guys, don't do that, 1 minus mu s tan theta. Good. Now that we have this expression, we know how to find the velocity now. Very easy. velocity in this case is easy. Now in this following term, what happens is if mu s is equals to 0, if coefficient of static friction, if there is no friction between the surface and the tire, like this F1 cars, if there is no friction between the surface and the tire, can the car still move at a maximum velocity? Let's see that here. If mu s is 0, this is 0, this is 0. 0 times tan theta, 0. So you get this v square, which is equals to, don't worry about the cycle race, we'll get to that, equals to rg tan theta. So v is equals to square root of rg. So even when there is no friction acting between the surface and the tire, the car still can move at a maximum velocity given by this, let's say v naught, which is equals to root of rg tan theta, right? So that is why the roads, you see, in case of a car races, they have banked, because the cars can move at a maximum velocity even when there is no static friction. In case of rainy season, there's rain on the track, but the car still moves at a good maximum velocity. Again, why? Is because friction is not really necessary when it comes to a banked road for it to move with a maximum velocity. This. Okay? So I hope I made this clear. Now, what happens when you go to the outer edge and the inner edge of the circular track? How can it differ? Because you have some cycles that move at the outer edge, or some cars that move at the outer edge. Some cars move at the inner edge. Who has a better advantage? You see, among the two, who will have the better advantage? Now, for that question, I leave it to you. I think you can explore about it. You can conduct a little bit of research and you answer the question, who has a better advantage for a person, for a car or a person who is moving along the outer edge of the racetrack or the inner edge of the racetrack? You try to answer that. But one thing I can assure you is, while moving on this outer or the inner edge, it creates a wear and tear on the tire. So this is what happens just 4 or 5 laps in case of a F1 race, F1 races or NASCAR races, 4 or 5 laps, and you will see the tire blistering. So much will be the friction between the tire and the surface, the ground. So this is what happens for a given tire, even when it is moving along the banked road. More frictional force and the tire starts to blister and wear out. So that is all I have for today. So in the next class, we shall discuss about solving a problem, the steps taken to solve a given numerical problem in mechanics. So I'll see you on the next session. Until then, take care and have a nice day. Bye-bye.